Welcome to the Deep Dive, where we plunge into a stack of information, extract the most powerful insights, and give you a shortcut to being truly well-informed. Today, we're taking a fascinating plunge into organic chemistry, specifically Chapter 9 of Organic Chemistry, 2nd edition, by Clayden, Greeves, and Warren. Our mission for this deep dive is really to explore the incredibly versatile world of organometallic reagents, and specifically how they become our sort of molecular architects, building new carbon-carbon bonds. Think of it as moving beyond the basic building blocks and really into the art of constructing complex molecular structures.
Exactly. Yeah, we're going to emphasize the mechanistic reasoning behind these reactions, tracing reaction pathways, seeing exactly how functional groups transform, and even getting an early glimpse into the strategic thinking behind retrosynthetic analysis. It's really about understanding not just what happens in the flask, but why it's such a fundamental step for making, well, virtually any complex molecule you can imagine.
Right. And why should you care about building these carbon bonds? I mean, we're talking about the bedrock of synthetic chemistry here. Imagine constructing life-saving drugs or developing cutting-edge materials with really precise functions, maybe even designing new agricultural tools. This chapter reveals one of the most important, I'd say, almost artistic tools in the organic chemist's toolbox for that exact purpose. For instance, in one synthesis of juvenile hormone, that's a key insect pest control agent, 7 out of 16 carbon bonds were actually made using organometallic reagents.
That's a lot.
Yeah. Or in an enzyme inhibitor, 8 out of 20 CC bonds were formed this way. These aren't just isolated examples. It's really the norm in complex synthesis.
Absolutely. And to set the stage properly, we'll definitely build on concepts you're likely familiar with. Things like electronegativity and bond polarization from Chapter 4, how Grignard reagents and organolithiums attack carbonyl groups. That was Chapter 6. And the deprotonation of CH bonds by strong bases from Chapter 8. Yep. These are really the foundations we'll use to understand the elegance of these reactions.
All right, let's open this toolkit then. So what is it about organometallics that gives them such a unique and powerful role in synthesis?
Well, the key thing here is the reverse bond polarity. Normally in something like a carbonyl group, the carbon is electrophilic, right? Because oxygen is more electronegative, it pulls electron density away.
Right.
But in organometallic compounds like organolithiums and Grignard reagents, the carbon-metal bond, it's polarized towards the carbon. Metals like lithium, magnesium, sodium, aluminum, they're significantly less electronegative than carbon.
Okay, so if the carbon effectively gains electron density, it acts as a nucleophile, right? It's like flipping the script on how we usually think about carbon reactivity.
Precisely. That carbon becomes electron-rich, ready to attack an electrophilic center. From a molecular orbital perspective, what this means is the highest energy electrons, the ones in that carbon-metal sigma orbital, they're actually more concentrated on the carbon. That's a fundamental orbital reason why the carbon acts as such a potent nucleophile.
I see.
And while we'll, draw them as simple structures for clarity, it's worth remembering that in reality, they often form these complex aggregates with solvent molecules.
Right, which can affect reactivity.
Exactly. That can influence the reactivity in subtle ways.
Okay, so we've grasped the fundamental power of these molecules. But the big question for any chemist is, how do we actually make them in the lab? What's the recipe for creating these chemical powerhouses?
Well, the classic starting point is Grignard reagents. Named after Victor Grignard, of course, who won the Nobel Prize for this work. They're typically made by reacting magnesium turnings with alkyl, aryl, or allyl halides. So that's iodides, bromides, or chlorides. And you do this in ether solvents. Common examples are diethyl ether, ET2O, or tetrahydrofuran, THF. Also dioxane or dimethoxyethane, DME. Those are the usual suspects.
And the magnesium literally inserts itself into that carbon-halogen bond. That sounds, well, pretty neat.
It is. It's a fascinating process. It's called oxidative insertion or sometimes oxidative addition reaction. Magnesium goes from its elemental state, Mg0, to its much more stable MgH oxidation state.
Yeah, okay.
And that stability, that's really the driving force. Now, to get it started, you often need a little push.
A push?
Yeah, like adding a tiny crystal of iodine or using ultrasound. That just helps remove the thin coating of magnesium oxide that's usually on the metal surface. Gets things going.
Got it. What about organolithiums then? Are they cooked up in a similar way?
Very similar, yes. Also via oxidative insertion, but this time using lithium metal with alkyl or aryl halides. Each reaction actually consumes 2 lithium atoms, forming the alkyl lithium and a lithium halide salt. Lithium, like magnesium, moves to a highly stable state, lithium in this case.
Okay.
A key difference, though, with organolithiums is that you can often use hydrocarbon solvents, things like pentane or hexane. This suggests they might have less need for external coordination compared to Grignards. Gives chemists a bit more flexibility, in their lab setup.
Now, I've heard some pretty wild stories about how reactive these organometallics are, especially with, well, common substances. Is it true they're just absolutely destroyed by even a tiny bit of moisture?
Oh, absolutely. That's not an exaggeration. They are incredibly strong bases, which makes them highly sensitive. They react rapidly and usually exothermically, so vigorously, with water and pretty much any proton source.
Well,
Think about methane. Its pKa is around 50. Basically, nothing will deprotonate it under normal conditions. But methyllithium, for example, reacts instantly with water to give methane back. The equilibrium lies vastly, vastly to the right. It vividly demonstrates just how much stronger the organometallic base is compared to its conjugate acid.
so yeah, definitely keep them away from your water bottle in the lab.
Exactly, lesson one. But this extreme basicity, while a handling challenge, makes them invaluable for deprotonating other weaker acids in organic chemistry, things you couldn't deprotonate otherwise.
Okay, so if they're such strong bases, what kind of organic compounds are they particularly good at deprotonating? You mentioned weaker acids.
Alkynes are a prime example, terminal alkynes
Mm.
specifically. They are the most acidic hydrocarbons with pKis around 25.
Why is that?
It's due to their hybridized CH bonds. The conjugate base, the alkynyl anion, is stabilized because its negative charge resides in a lower energy s orbital, which has more Sid character and is closer to the nucleus.
Ah, okay. Makes sense.
So strong bases like butyllithium or ethyl magnesium bromide, even sodium amide, NaNH2, can easily deprotonate them. And this yields metal derivatives of alkenes, alkynyl anions, that are themselves potent nucleophiles, ready for the next synthetic step.
Can you give us a real-world example of where this deprotonation, then nucleophilic attack strategy is actually used, like in making something important?
Certainly, alkylolithium and magnesium compounds are really crucial in some very important syntheses. For instance, a key step in making the antibiotic erythronolide A uses this, or the widespread natural product farnesol. Even ethinyloestradiol, that's a component in almost all oral contraceptive pills, is made by adding an alkylolithium to ostrone. It's a foundational reaction for building complex natural products and pharmaceuticals. Really fundamental stuff.
Wow, okay, so it's not just textbook chemistry, it's really out there.
Definitely. And while deprotonation is a major route, it's not the only trick organolithiums have up their sleeve for making new organometallics. They can also undergo something called halogen metal exchange.
Halogen metal exchange, so they just swap places.
Pretty much. The lithium and halogen atoms simply swap positions.
So if I have, say, butyllithium and bromobenzene, I can essentially swap the lithium for the bromine and create phenolithium and butyl bromide.
Exactly.
But why would that reaction spontaneously occur? What's the driving force there?
That's a great question. It comes down to equilibrium and the relative stability of the carbanions involved. Benzene had the pKa of about 43, while butane is way up around 50.
Okay.
This means the phenyl anion, the conjugate base of benzene, is significantly more stable than the butyl anion. So forming the phenolithium product is thermodynamically favorable. That stability drives the exchange forward.
I see. So the more stable anion wins out.
Precisely. And this method is incredibly useful for making more substituted organolithiums, like vinyl lithiums too. It tends to work faster with bromides or iodides compared to chlorides, by the way.
Good to know.
And beyond that, there's one more method worth mentioning: transmetallation. This is where you take an organolithium or a Grignard and convert it to a different, often less reactive organometallic. You do this by treating it with the salt of a less electropositive metal. Zinc salts are a common example.
That's interesting. Why would we want a less reactive organometallic? Aren't we usually chasing the most reactive species for making bonds quickly?
Not always. Sometimes that high reactivity, especially the strong basicity of Grignards and organolithiums, can be, well, a double-edged sword.
How so?
They can lead to unwanted side reactions. For example, with very strong electrophiles like acid chlorides, they might just deprotonate something nearby instead of adding cleanly to the carbonyl.
Ah, okay. Competing reactions.
Exactly. Less reactive reagents, like organozinc compounds, allow for much more controlled and selective reactions in those cases. E. Negishi, who won a Nobel Prize, did pioneering work at organozinc chemistry, recognizing precisely this strategic advantage.
So it's all about control and precision then. Choosing the right tool for the specific job, even if it's less reactive overall. That's clever. Okay, now that we understand how these powerful reagents are made, what makes them tick, and why we might even want different reactivities. How do we actually use them to build molecules? What's the core application in synthesis?
Well, the core principle, the bread and butter, is that organometallic additions to carbonyl compounds typically lower the oxidation level of that carbonyl carb.
Lower the oxidation level, meaning?
Meaning if you start with an aldehyde or ketone and add an organometallic, you generally end up with an alcohol after workup. More specifically, if you add them to carbon dioxide, you get carboxylic acids. Additions to formaldehyde give primary alcohols, other aldehydes give secondary alcohols, and ketones yield tertiary alcohols. It's quite systematic.
Let's break that down. Carbon dioxide first.
Right. Reacting an organolithium or a Grignard with CO2, often just bubbled through the solution or poured onto dry ice, gives a carboxylate salt. Then, upon acidic workup, adding dilute acid, you protonate that salt to get a carboxylic acid with one additional carbon atom compared to your starting halide.
Okay, but that sounds like multiple steps.
It is. It's a crucial three-stage process.
Yeah.
First, you make the organometallic. Second, you react it with the CO2. Third, you do the acidic quench. And critically, you have to absolutely avoid water until that very final step. Any water getting in too early.
It kills your reagent. Got it.
Exactly. Poof, gone.
And if we use formaldehyde, that's the simplest aldehyde, CH2O, what kind of alcohol do we get then?
Formaldehyde uniquely adds just one carbon atom and produces primary alcohols. There was an elegant example in that Cecropia juvenile hormone synthesis we mentioned earlier, involved this exact transformation, adding that crucial single carbon.
Okay. And other aldehydes, like acetaldehyde or something bigger.
Other aldehydes, the general formula RCHO, they react to give secondary alcohols. While ketones, which have two carbon groups attached to the carbonyl carbon already, they yield tertiary alcohols.
Right, adding one more R group.
Precisely.
Okay, this brings us to an interesting point. When you're aiming to synthesize, say, a secondary or tertiary alcohol, it sounds like you might have choices.
Absolutely. That's an important strategic question for synthetic chemists. For a secondary alcohol, there are often two distinct possible routes. For example, you could make a specific secondary alcohol using, let's say, isopropyl magnesium chloride and acetaldehyde. Or you could use methyl magnesium chloride and isobutyraldehyde. Both give the same product.
So there's significant flexibility, like a chemical puzzle with multiple solutions. How do chemists actually decide which way to go in the lab? Is one better than the other?
It often comes down to practical factors, really. Which route gives a better yield? Which starting materials are cheaper or more readily available commercially? Sometimes, honestly, you might even have to try both routes in the lab to see which one performs best in your hands.
Practicality wins out.
Often, yes. It's not just about what's theoretically possible on paper, but what's practical and efficient in the real world. And for cyclic alcohols, by the way, just reducing the corresponding ketone with something like sodium borohydride is also a great alternative to consider. Different pathway, same product.
Good point. And for tertiary alcohols, I imagine there's even more choice, offering even greater strategic depth.
Yes, typically three distinct routes. You can swap which group comes from the organometallic and which two are on the ketone. We could illustrate this with a step in the synthesis of the natural product neurolytyl, but the key takeaway is understanding that these alternative combinations exist. This idea of working backwards from the molecule you want to make, identifying the bonds you need to form, that's called retrosynthetic analysis.
Ah, yes. Thinking backwards.
Exactly. It's a really powerful concept, the art of molecular design, and we'll explore it much more deeply in Chapter 28.
Okay, looking forward to that. So we've mastered how to add carbons and make various alcohols. What if we want to reverse that process? Or maybe change the functional group entirely, say, converting an alcohol back into a carbonyl?
Ah, that's where oxidation comes into play. To oxidize organic compounds, increase the oxidation state, we typically need transition metals that have access to higher oxidation states. Chromium is a real standout here, specifically its Cr3s and Cr5 forms. Those bright orange CrVi compounds are excellent oxidizing agents. They work by removing hydrogen atoms from the organic molecule, and in the process, the chromium itself gets reduced to the green chromium-3, Cr3. That color change is often a nice visual cue in the lab.
Okay, chromium. What are some of the specific chromium reagents a chemist might reach for on the shelf?
Well, the most common ones include chromium oxide, just CrO3, also pyridinium dichromate, PDC, and pyridinium chlorochromate, PCC. Those last two, PDC and PCC, are often preferred because they dissolve better in common organic solvents like dichloromethane, which makes them a bit easier and safer to handle.
And what do these reagents do specifically?
They allow for really precise transformations. Primary alcohols can be oxidized to aldehydes. Now, if you use stronger oxidizing conditions or different reagents like calcium hypochlorite perhaps, they can be further oxidized all the way to carboxylic acids. But PCC and PDC usually stop nicely at the aldehyde stage.
Okay. And secondary alcohols.
Secondary alcohols are cleanly oxidized to ketones. And critically, tertiary alcohols.
Right.
They cannot be oxidized using these methods without breaking a carbon-carbon bond
Why not?
because they lack the necessary hydrogen atom on the carbon that's bearing the hydroxyl group. That hydrogen is essential for the mechanism to proceed.
Ah, okay. The mechanism requires that specific hydrogen. So these oxidation steps involve removing hydrogens or effectively adding an oxygen bond. How exactly does the CRVI do this? What's the magic behind that orange to green color change?
Well, the accepted mechanism involves forming an intermediate called a chromate ester.
Huh?
First, one hydrogen is removed from the alcohol's OH group to form this ester linkage to the chromium. Then a second hydrogen, the one on the carbon atom bearing the oxygen, is removed in a concerted, often cyclic process. In this step, 2 electrons get transferred from the organic molecule to the chromium, reducing it from CREI down to ultimately HER3, or related lower oxidation states. It's quite an elegant, well-understood pathway.
And this creates an incredible cycle for synthesis, doesn't it? You can make an alcohol using an organometallic, then oxidize it to a ketone, and then maybe use another different organometallic to add again and build a completely new tertiary alcohol. It's like a molecular Lego set.
Exactly. That's a great analogy. It creates a powerful iterative cycle for building increasingly complex molecular structures, adding complexity one carbon bond, one functional group transformation at a time. We've just looked at these key interconversions, going between ketones, aldehydes, and alcohols by forming CC bonds using organometallics, and then how oxidation and reduction perfectly complement these methods. This is really the heart of constructing complex organic structures from simpler starting materials.
Wow. What a deep dive. We've truly unpacked the vital role of organometallic reagents in forming carbon-carbon bonds. Everything from their fundamental polarity and how they're actually synthesized in the lab to how they're strategically applied in creating, well, everything from carboxylic acids to primary, secondary, and tertiary alcohols. It really shows how you can design and build molecules.
And we also saw how complementary oxidation reactions, especially with those chromium-based reagents, allow us to transform alcohols back into aldehydes and ketones, opening up even more synthetic possibilities. This ability to interconvert functional groups is just as crucial, really, as building the carbon skeleton itself. It gives you control.
Yeah, that idea that we study organic reactions, not just for their own sake, academically, but so we can actually use them to make things from life-saving drugs to everyday materials. That truly highlights the elegance and the utility of organic synthesis. It's where chemistry really transcends from just observation to intentional creation.
It truly does. And this is just scratching the surface of these powerful tools.
Hmm.
We'll broaden our horizons to other carbonyl compounds in future chapters and delves much deeper into the art of designing molecule syntheses in Chapter 28, that retrosynthesis part, and even explore more complex organometallic methods way down the line in Chapter 40. This is really how you take abstract chemical concepts and turn them into tangible, useful creations.
So, what seemingly simple reactions, when you truly understand the why and the how, actually hold the key to building the most complex structures you can possibly imagine. Definitely something to mull over until our next deep dive. Thank you for being part of the Last Minute Lecture family. We look forward to diving deeper with you again soon.